Great. So I've got 10 minutes to give you sort of just a brief overview of where we are and what the plans are going forward, but also want to use it to touch upon something that Brian mentioned, which is, by this time next year, I think, hopefully, this might be wood, we should have seen several landers on the surface, and we're going to be showing and analyzing new data of the surface. And so I show here the nominal IM plan. So the first three here, IM1 to IM3, are funded to go. IM1 is predominantly the NASA payload portion is from LSIP-P. IM2 was the Prime 1 task order. And then IM3, as Dave touched upon, was one of the first PRISM selections. And sort of the takeaway from this is that our plan is to try and provide access to the lunar surface with a cadence of at least once per year. And I think that's an important takeaway as you try and plan the experiments that you want flown, that you can fly, you can learn, and then you can fly again. The other takeaway I wanted to show is the approximate breakdown between the payloads, in that when CLIPS was first started, the idea was NASA would provide enough payloads to merit these deliveries to occur. But the hope was that this would instigate the beginning of a commercial market, with the long-term goal that there would be a certain number of providers flying payloads from NASA and other companies. And I think and other companies have found this too. When you look at the breakdown, it's been very pleasing how much non-NASA payload there was already there, and interest being ready to fly. And while some of the initial payloads were sort of standalone entities from a scientific goals perspective, again, as Dave showed with PRISM and with the other PRISM selections, I think from a scientific perspective, we're heading into a very exciting territory where PIs can propose 2 or 3 instruments to do detailed, focused, decadal level science anywhere on the moon that they want to go. So a little bit about our primary lander, which is Nova-C. The first 3 deliveries that you'll see from us will all use the Nova-C. It's a fairly tall lander. It can go anywhere on the moon. It can carry anywhere from 130 to 250 kilograms of payload, and your experiments can be placed in multiple mounting locations depending on what your field of view needs are. We also have designs for, the goal here is to try and support all science and exploration needs, and not everything fits into a 130 kilogram box. And so we have a Nova-D design, which is a derivative of Nova-C, and there are variations on that depending on the lander and the booster that can, in fact, with the Nova-D Heavy, go all the way up to 2,500 kilograms. Just one slide on our first mission, IM1. You can see the NPLP payloads from NASA that were selected, including scalps and roses that you just heard about. And then you also have the commercial payloads, and there are a wide variety of sort of scope and style for those payloads. We also understand that many of our customers want their experiments or instruments to fly, have mobility. We have teamed with Lunar Outpost, who are based in Golden, Colorado, to provide that surface mobility. They have a range of rovers depending on our customers' needs, how far they need to go, the type of terrain they need to deal with, whether they need to survive the night. In our early missions, you'll predominantly see the MAP rover. Again, this is one that's flying, carrying Lunar Vertex, for example. That can carry about 12 kilograms of payload and travel about 10 kilometers. But also, it should be clear that any given lander can carry more than one. There's enough mounting points that we can have, and we will see, in fact, multiple rovers on our missions. One of the things I think particularly exciting to see demonstrated on our second mission is our hopper capability. Hopper is something that was developed as part of a Space Technology Mission Directorate tipping point proposal. You can think of it as a small lander that gets delivered to, its mission doesn't start until it's delivered to the lunar surface. It has the ability to carry about 8 kilograms of payload, about 25 kilometers. And the key thing is it can do extreme access. It can go to places that a rover either can't, or it can do it much faster than a rover. So it's designed to explore inside lunar pits, to go inside lunar lava tubes to have a look. It can cope with rough, blocky terrain, so it could go, for example, to the floor of a deep crater quite quickly, quicker than a rover could, and also to access permanently shadowed regions. Again, providing very precise regional exploration. I mentioned the first one. The demonstration is going on IM2. This is an image that Mark Robinson made from a NAC image. It will land on the Shackleton de Galash Ridge. These names, anyone who knows your history, these names are from the Shackleton exploration era, the names that Mark likes to use for these craters. And so even though this is a technology demonstration, we are trying to get some science from it. We've added a radiometer, a neutron spectrometer, and several cameras. And so, yes, we will land on the ridge and take a number of hops, demonstrate different capabilities, including a sort of a typical parabola, but also the ability to fly, traverse at a constant altitude if that's what the measurement needs. It's also our intention to hop into a small permanently shadowed crater, take some measurements, first ever measurements inside the permanently shadowed crater in situ, and then hop back out and warm up. Satellite delivery service, whilst doing delivery to the lunar surface, we have the ability to drop off orbiters of different scales in different locations. We can drop fairly large payloads off in a TLI type or translunar injection orbit, but also we can drop smaller orbiters up to about just under 400 kilograms into a 100-kilometer circular orbit. And that has got us, and in addition to that, we're putting up our own communication network. Starting with our second mission onwards, we'll be dropping off a satellite en route and gradually building up our own ComNav capability using Earth ground stations dotted around the world. So because of that, two things that we are exploring is the possibility of doing our own small reconnaissance orbiter. What got us thinking about this is the fact that we can drop something off in a good mapping orbit of 100-kilometer circular, as well as using the communication relays, allows us, we think, to do more with less, in that a fairly modest size spacecraft, potentially even CubeSat scale, because it only needs enough delta V to survive in that orbit and enough power for the radio to talk locally, that we could get some interesting data sets for exploration, resource, and the science community. And so that's something we are actively looking at trying to do in the next 2.5 to 3 year timeframe. Related to that is an idea we're exploring, which would be a multiple CubeSat mission. If we can either do our own or have enough interest in the international community to fly some lunar CubeSats, then our goal would be to sort of dedicate a fair amount of resources associated with a future lander delivery to do a multi-CubeSat mission. And we think this has lots of advantages. We think it's an opportunity to really exploit the ingenuity of the science community. CubeSats are something very doable at the university level. So we can leverage the lunar community expertise, use it as a way of growing the next generation of scientists and engineers with real flight experience, good international collaboration opportunity, and it still says 9. And then also could be multidiscipline. It could be stuff other than just lunar science. Thank you.